All right, so we started 2-6 already. This would be part 2. Okay. Yesterday we talked about adding in exponential, which we've already talked about, but it was like specifically assigned to this section, which was adding an exponential as a possible model when you are given a set of data. So if you're given data and you're given the calculator, you can of course run your regression and you can add exponential in there as an option. You can look at your R-squareds. You can also do it from your coordinate points without your calculator. So it's important to know how to do it both ways. If it's linear, then you subtract the first rate of change is the same, then it's linear. If you do it again, second rate of change is the same, or second difference is the same, then it's quadratic. And quadratic is the only one that can repeat a y. So if you're looking at a set of data and a y repeats, quadratic is the only one that can do that, right? Like if it's linear, it's either rising or falling as it moves from left to right. You can never get a repeated y. If it's exponential, it's either rising or falling as you move from left to right, but you can never repeat a y. The quadratic, being the parabola shape, is the only one in which you can see a y repeat. So if you get a set of data, you can also use that as a differentiation. Then we worked through these examples, and we started talking about the residual and residual plot. So as a reminder, okay, on the left-hand side, this is what your original collection of data would look like. So this is if it is plotted on your stat plot. Each of those dots represent actual data. Then they ran a linear regression, and the line is the linear regression model. Everything that if the dot is above the line, we say that the line is an underestimate. If the dot is below the line, we say the line is an overestimate. So the line represents the prediction. Predicted was underestimated, prediction was overestimated is what you'll compare, okay? The R is the value that is the actual minus the predicted. So the actual is data you get from your chart, whereas the predicted would be like your F of that number. So I would find the regression, I would predict what would happen at that by doing F of whatever, and then you're gonna compare the actual data to that. Then the right-hand side, this is your residual plot. So the residual plot took that line, in this case, that regression line, and it made it its x-axis. If this was a quadratic model, it still makes it the x-axis. If it's a cubic, whatever it is, it doesn't have to be a linear model to make it in residual. It still makes it the x-axis. Everything above it would be data that would have been above the line. So the dots that are there, the line is an underestimate, and then the dots that are below it, the line is an overestimate, which means the model would have been an overestimate. All right, we talked about appropriate and inappropriate model. If there is a pattern, so this guy has a pattern here, it looks kind of like that, then this is a not appropriate. If there is a scattered of dots, then that means that model is appropriate. So in this case, we said that the left side would have been appropriate, yes, and the right side is not appropriate. There's definitely a pattern there. These could happen like that. It could give you, what will happen is it will say like, here's a graph, and then it will say which of the following pertains to it, and it will give you 4 choices. And the 4 choices might be, it is appropriate because there is a pattern. It is appropriate because there isn't a pattern. It is not appropriate because there's a pattern, or it's not appropriate because there isn't a pattern. So you would pick based on which one of those you intended, but that's how they will come up with 4 choices. Or it would be a multiple choice question in which you'll get 4 graphs, and it'll say which of the following are appropriate or which of the following are not appropriate. Okay, now let's look at this one. So what are we on? Example 3. Let me get rid of the toolbar. Example 3 says the graph shows a bivariate data set and its least squares regression line. The regression line is called a least squares regression line. We call it a regression model or the model, okay? And the question says, which of the graphs shows the residual plot for the same data set? So remember that line becomes your x-axis. Every dot above the line should still be above the x-axis, and every dot below should be below. So if I just honed in on like 1, for example, if you look at 1, your point is above, right? It's above the model, which means if I go to my choices here and I go to where 1 is, I would look at the x that is above the model, and that happens at C. Let's say there were 2 where it happened, then I would go to where my model value is 2, and where my model value is 2. My dot is below the model, which means my dot would have to be below the model. So this one's above, this is the only one below. It was enough to eliminate, but if I would have needed to keep going, I would have just keep checking, okay? So that's how you go from actual data to your residual plot. All right, so we have talked about this. Remember earlier I said last year we waited to introduce R-squareds until now because this is where the content brings it in, but I just said why wait this year? You need to know it anyways. So we actually already did this, okay? Use the graphing calculator to find your R-squared, and your R-squared that is closest to 1 is the appropriate model. If your R-squared is 1, then it's a perfect model. If you had a residual plot in which you had the line and every single dot was on that line, that is a perfect model, okay? It doesn't happen very often, but if you wanted to identify what it looks like, it would look like that. The R-squared, if it's like 0.9497, it means that 94.97% of the variation in the dependent variable is explained by the variation in the independent variable. So it's just that it would be like, 1, it can't be a pattern, and 2, if there is an error, that 94% of that error is explained by the model. Okay, sorry, I'm going to have to say it again. The college tuition in the United States has increased by 1,200% since 1980. So 1980 is our T equals 0. So this would be 0, 10, 20, 30, and 40. And then it asks you to find the model that best fits the data. I'm going to give you 3 options. It will usually give you your options. So I'm going to do linear, quadratic, and exponential. And we're going to run them. So linears, R-squared is 0.909856. Quadratics, R-squared is 0.9942. So already we know quadratic is better. Stat edit, go to exponential. And exponential is R-squared equals 0.993. So of these 3 models, which one is the best one? Quadratic. And now I'm going to go back. I can either, so here's the tip, like you get to choose what you do here. You can either rerun the one that's the best one. I could go back and rerun quadratic. Or I could have stored like y1 as linear, y2 as quadratic, y3 as exponential to use it. But I would think it's just as fast to rerun it. So I'm going to rerun my quadratic. I'm going to store it in my y1. And I get my model would be y equals 4.6728, which becomes 3x squared, minus 5.334x plus 2008.771. That is your best fit model. Everybody with me so far? Yes? No? Yes? Okay. Then it says compare the predicted cost of a public university in the year 2010 to the actual cost. So from the chart represents what? The predicted cost or the actual cost? The actual cost. So 2010's actual cost is $5,814. To find the predicted, I'm going to find y1 of 30. So y1 of 30 is $6,054, and this is dollars, right? $6,054.31. So what's bigger, the actual or the predicted? The predicted, which means my model would have been over my dot, right? Which means my model was an overestimate. So I know I'm going to mention that. So I make sure I make a note of it, whatever. But I know that the model would have been over the actual. The R, because that could be asked of you, is the actual minus the predicted. Actual being 5,814, predicted meaning 6,054.31. So 5814 minus 6054.31. And my R is a negative 240.31. Remember, if R is negative, the model is an overestimate. If R is positive, the model is an underestimate. You with me so far? So here's what's important. The wording says, what does it mean in this context? When it asks for in this context, it means you have to include it specific to these units. So we are talking about the year, and we are talking about the cost of tuition. So we would say something along the lines of, in the year 2010, because that's the year that we're specifically talking about. So in 2010, which is our input, the model overestimated the cost of tuition by $240.31. So you have to give the input, which was the 2010. You have to give the over or under estimate, and you have to give the amount that it over or underestimated by. All right, putting it all together. This says calculate the following regressions using the data provided. It's asking you for the linear, the quadratic, the exponential. Then it's asking you which of the model is best fit. Then it's asking you to predict the enrollment for year 2010 and compare it to the actual enrollment, and what does it mean in this context. Notice that all you're given is a chart this time. It doesn't tell you where T of 0 is. If it doesn't tell you where T of 0 is, make the first one T of 0, okay? So we're going to say that the 1970 would be 0, which means 1980 would be 10, 1990 would be 20, 2000 would be 30, 2010 would be 40, 2015 would be 45, and 2016 would be 46. And then you're going to put all the information in. So I go into my edit. 0, 10, 20, 30, 40 is already there. So I add 45 and 46. And then now we're talking about college enrollment in millions. Just keep it in millions. So 6.3, 10.5, 12, 13.2, 18.1, 17, 16.9. And then it actually wants you to run each of those regressions. So I'm going to run them, but I'm also going to like note on the side the R-squareds. So calc, linear, and I'd get y equals 0.229 x plus 7.170. And my r squared is 0.93885, so on. Then I'm going to run the quadratic. Y equals negative 0.002, because it's 1/6, x squared, plus 0.3109, which becomes 1, x, plus 6.659. And my r squared is 0.94647. So better than the linear already. Then I'm going to run my exponential. I'm storing it each time just in case so that you know to. And I get y equals 7.4489, so 9x plus, no, not sorry, plus, not the x is not there, times 1.0198, so the 8 bumps the 9 and the 9 bumps the 2 to the x. And this r squared is 0.905. So of these, which is the best fit? Quadratic was my best fit. And then find the predicted enrollment. So I'm going to go back, run. So here's an option you can do. If you don't want to rerun them, you can store, let's say you can store linear as y1, you can store quadratic as y2, and you can store exponential as y3. And then when you find your predicted enrollment, you could always use whichever one was the best. Does that make sense? So instead of rerunning, it's just fast to rerun it in my opinion, but instead of rerunning it, that's definitely another option, is store them in different y's and then make sure you pick the right one. So y1 of 2010 was 40 years after. 16.407 million was our predicted one. So what happened? Is my predicted bigger than the actual or less than the actual? Predicted was less than. So it was an underestimate. Okay. Specifically, the actual is 18.1 minus 16.407. My R is a 1.693 million. So in the year 2010, the model underestimated the enrollment. Is it college enrollment? Yeah, college enrollment by 1.693 million students. People, students, whatever. Questions? All right, that's it.